So this is a recording of the lesson that we did on April 4th of 2014, and we're talking about gas laws. And as kind of a starter in this area, the ideal gases, there isn't anything that is an ideal gas. And this should go down on top of, or below, it should be at the bottom of your little handout that you got today, which has all the conversion units for working with gas laws. So one of your homework assignments is to watch this video that there's a link to on, here, let's go to Friday. So this link right here, is it? Oh, yeah, that's offsite. Okay, this is called Ideal Island. And Ideal Island is kind of hokey, but it's a pretty good little thing, and it will help you understand what an ideal gas is supposed to be, which is good because it makes it less of just a number and a formula. And the Zumdahl pages that you need to do for homework, since you can't take the Zumdahl books home, I've given you a link right here that shows you all the problems as well as the answers, which is very nice to have, so you can check yourself. And then here's the handout that I gave you today, and I think that's everything. Yeah, okay. So let's go back and get this copied down, and I will stop the recording for a second. So what this says is that at higher temperatures or lower pressure, or both, that ideally, for an ideal gas, right? Ideally, you would have both situations, a higher temperature and a lower pressure. Okay, this page shows you all of the variables that we have in the gas laws. So P for pressure, V for volume, N for moles, and T for temperature. The only one that requires you to be in a specific unit of measure is temperature. It always has to be in Kelvin, no matter where you use it. And there's only one constant in all these gas laws, which is kind of nice. And we'll talk about this constant later, but for right now you want to write that down so you're going to get used to using it. It's 0.0821. And the units of measure for this are substantial, but we normally don't even use them. But we'll talk about that next week. So here's the extent of our notes for today, and that's going to hold you to go ahead and do the problems that we're going to do in the homework. Now on page 408 of the Zumdahl textbook, I'd like you to all turn there right now, and we're going to have some practice problems in there to get used to the units of pressure. And all units of pressure can be converted with this string of equalities. So within this guy, all of these things are equal to each other. But you have to have the number that you see here. Like, for instance, if you're dealing with torrs, you have to have the 760. If you're dealing with millimeters of mercury, oh, look, it's the same number. Why? Mr. Torricelli just had to get his name into the act. And that's where torrs comes from. And then Pascal's, of course, that was Mr. Pascal, or Dr. Pascal probably. And he had the Pascal and kilopascal units. And when you go to the gas station and you fill up the tires in your car, you're going to see PSI. And most tires are inflated to roughly what, 30 PSI, pounds per square inch. And I don't think on your handout you had these listed as units of pressure. Okay, so why don't you put that on the end of it? I put a blue box around it to make it make it stand out a little bit more. Let's see. Oh, I made it stay. I put it on a. If you look in your textbook, on page 408. Would you please check that out while I call you by name to see if we can get these calculations done? And Lucine, you get to go first. Would you please tell us, if I'm converting to atmospheres, what am I given to convert into atmospheres? Page 408. You can't do it if you're not looking at that page. That's the fine. What's the given? Now you got it. Okay, 657 what? Millimeters of mercury. Okay, so what is the first fraction going to look like? We start the calculation like we've started calculations since August. There you go. Excellent. Now for this next one, you're probably going to need a little bit of help. But Robert, since you're the one that's going to be answering it, you want to pay special attention. Okay. So, Robert, why don't we have you help us out here? What are the 2 units of measure in this problem? You don't have to look there. It's up here.
Are millimeters?
No. Millimeters of? Okay. That's this guy right here. Now I'm circling these. Don't you do that on yours, because you're going to use this over and over again. But I can erase easily. So, now, if you have millimeters of mercury, what else do you have? What are you going to convert to? What unit of pressure? Read the problem, man. Well, then read it out of the textbook. Okay, finally, we got it. Atmospheres. Okay, atmospheres. Now, if I'm circling those 2 because that's your given and find. Whatever your given and find are, those are going to give you a conversion factor because they're equal. If I was going to, right now we're dealing with these 2 units of measure, but it could be millimeters of mercury to psi. And that means that 14.7 psi is equal to 760 millimeters of mercury. Okay? So let's stick there with the 760 and the 1, and let's look at what the fraction will be made from. 1 atmosphere is equal to 760 millimeters of mercury. So now your question is, what's on the bottom of the fraction that's going to go right here?
The bottom of the fraction, the denominator. Would be mercury.
Okay, what's the number that goes with mercury?
1.
I don't think so. 760. Okay, what's going to be on the top?
Would be 1 millimeter.
You have this on your paper. Now, do you see it? Yeah, you just can't see it back there. Don't laugh at him. That'll get you sentences. Don't ever laugh at anybody in my class. I don't like it. Okay, so now all you do is run the numbers, and there's your answer. Okay? 7B, C, and D will be exactly the same. The next thing I want you to do always is cross out your units of measure, millimeters of mercury. And then when you get to your answer, you can see the only unit of measure left is ATMs. And that's what you have in your answer, and I want you to box your answers so they look like this, or circle them, either one, I don't care. Now, let's go down here and leave space. because you're going to have to put 3 problems exactly this size in there. All right? I don't think you need that much space, but I'd leave at least 4 or 5 spaces. Now, we're going to convert millimeters of mercury. Let's get someone else involved. Daniel's not here, right? Okay, so Arthur, what is my first fraction going to look like on this guy? What? Okay, 1045 what? Okay, 1045 atmospheres, is that what it says? In letter A? Okay, so let's go ahead and look. Very good. You got us off to a good start. David Centurion, what are we going to have on the bottom of our next fraction? 1 ATM is atmospheres, not atoms. And so, what's going to be on the top? What are we converting to? Absolutely. So, we're going to that guy. And that's what will be on the top. And that's all there is to it, folks. Just cross it out. How is this different from the first problem? Look. Yeah. As you see, this fraction and this fraction are upside down. Why? Because here we started with atmospheres, so atmospheres had to be on the bottom. Where here, we started with millimeters of mercury, so millimeters of mercury had to be on the bottom. Okay? Good thing to point out and realize. And then you have a multiply problem, and that's it. So circle your answer or box it, and you're done with that guy. Let's move on. Raphael, what's going to be my first fraction? Well, just look at the problem. It's right there in front of you in the book. We're doing a 12A. What's on? Oh, yeah. 1506. Is this what you're saying? I couldn't hear you. Okay, so 2.07 times 10 to the 6th pascals. That was the given. Very good. That got us off to a good start. And so soon. What has to be on the bottom of the next fraction? Okay, you're using this number right here, correct?
Yeah.
Okay, and what's going to be on the top? 1? We're going to KPAs. The only guy that has 1 in front is atmospheres. So what do we have to have on the bottom?
101.2.
I don't think so. How are you going to cancel this guy?
101, 100,000, 300.
There you go. Okay, that's the bottom. Okay, this is the top. Yes, that will work. I want to show you something that at least calculation-wise is easier, but you may want to use that other method anyway, because both will give you the same answer. So let's look and see what I was going to do. Let's get this out of here. This is going to be, I'll just expose the whole answer for right now. And let's look at this. 1 kilopascal. What does K stand for?
Temperature.
No, the temperature K is a capital K. Okay? But this stands for kilo. What does kilo equal to? 1K is equal to what? 1,000. Yes. So the 1,000 is what we need to substitute in the equality. So I'm going to say 1,000 instead of a kilo. So the kilo that is in this guy becomes 1,000 on the other side, and then I go ahead and put in the pascals. Okay? And now that's our fraction. Can you see that? 1,000 is here, and this 1,000 is equal to 1 kilopascal. So that'll work. The other one will work. Either way, whichever you like. Now, if you don't understand this guy here, why did this go away, and why did that thing go to 10 to the third? How come? If I do 10 with an exponent, what would the exponent be to replace the 1,000? 3 zeros. Okay, so when I divide this into this with the exponents, you're subtracting. Okay, so that's why we get 10 to the third. Right, what I'd like you to do now is get out your handout and do the copying of this right onto that paper. Okay, back to the recording now. Here we are looking at a problem that has V, P, a second V, and a second P. Now, the way they've lined these up, these guys over here are together, and these guys over here are together. And so I'm going to call this V1, P1, V2, and P2. Now, I wrote those as superscripts because I have the lines over the or underneath those things. But here's what this corresponds to in the original gas law formula, the combined gas law. See, V1 and P1 and P2 and V2. Now, do you see anything about N and T in this problem? Okay, what that means is that N and T are constant. They don't change. So if they don't change, and N1 is equal to N2, and T1 is equal to T2, that means they're going to cancel each other. So we can just get rid of them. So now we have the ability to write what is called Boyle's law, which is P1 V1 equals P2 V2. And when you do this, be sure that you use your variable in the unit of measure that you see here, or the kind of unit of measure. So we have a P1, right, and a V1? Okay, so P1 is 785 millimeters of mercury, and P2, or I'm sorry, V1 is 500, or not 500, but there we go, 53.2 milliliters. Okay, that's a unit of volume, and that is equal to, V2 is our unknown, isn't it? But we'll do P2 first, because that's the way it is up in the formula up here. So this P2 is not an unknown. P2 is 700 millimeters of mercury, and we're going to multiply that by the V2. Please, for your own sakes, don't use X for your unknown. And the V2 should be a subscript. Okay. Yeah, because that tells you what you're actually finding is the second volume. And now it's just a matter of multiplying it out. Okay, so all the answers are going to be given to you in the whiteboard file. I think that's on the next page. There you go. All the questions and answers are on the whiteboard file in the PDF online, and they will also be a link in tonight's homework page. So if you go to the website and you click on Friday, the 4th of April, 2014, you'll get our handout. You will get the Big Bigger. You will get this link that takes you to the educational portal and allows you to watch the thing on come on, this is the island thing, okay, the ideal island. And the other thing you get here is the same questions and answers that you're doing for your homework tonight. So that's available to you online. If you don't have online, you need to be sure and print it before you go this afternoon. That's it. Save it.